We have got an exciting lesson today. We are going to be going through everything you need to know about multiplication and division. We're going to go through a multiplication method looking at a 4-digit times a 2-digit. We're going to look at short method with a 2-digit divisor. We're going to have a look at inverse operations and BODMAS, which is the order of operations. We're going to look at multiplying and dividing by 10, 100 and 1000. We're also going to look at prime and composite numbers. Then we're going to look at prime factorisation, which is pretty tricky, before looking at our lowest common multiple and highest common factor, which is going to be very useful for most aspects of maths. Then we're going to look at square numbers and cube numbers, before finishing with two very important laws or rules that we need to know in maths. First, the commutative law, and then the distributive law. But let's not waste any time. Let's jump straight into our first lesson, which is going to be looking at multiplying a 4-digit by a 2-digit number. Let's go. Okay, so the example we're looking at is 3,465 multiplied by 23. And if we just look at our steps to success, the first thing we need to do is make sure we arrange our columns and make sure we put our titles on top of those columns so that we don't put a number in the wrong place. Then we're going to partition the question. We'll understand what that means in a minute. Then start with the smallest value on the bottom row and work our way up. And finally, we're going to add it all back together to get our final answer. So let's think about how to set this question out. We have 3,465 times 23, so I'm going to need to put my place value labels on the top. So I'm going to have ones, tens, hundreds and thousands, and then I can start to put my numbers in place. And I can put 3,465 and then my 23, I can see I've got 2 tens and 3 ones. Put my equals line, my multiplication sign, and I'm ready to begin. Let's tidy it up. There we go. The next step said to partition my question, and we're going to partition specifically this bottom row, and we're going to look at it as a 3 and a 20. So this row here is going to be answering the question 3 times 3,465, and then the second row is going to be answering the question 20 times 3,465. So let's work on our first row first of all, multiplying 3 times 3,465. But again, we're going to do it in small chunks. Our first chunk is going to be 3 times 5. 3 times 5 is 15, but I can't put 15 all in one column like that, because remember, one column, one number. So what can I do? Well, I can put my 5 in here, because we have 5 ones, but then my 10, I'm going to hold a small 1 here, ready for when I answer the tens column, which I'm going to do now. Then I can do 3 times 6. 3 times 6 is 18, plus my 1 is 19, but the same rule applies, so I can put my 9 in here and carry my 1 across. Top tip, scrub out that 1 that we've just used, so that we don't add it up by mistake later. Now I can do my hundreds column, which is 3 times 4. And 3 times 4 is 12, plus my 1, 13. Same thing again, small 1, big 3, scrub out the 1. Now lastly, I can do 3 times 3 for my thousands column, and 3 times 3 is 9, plus the 1 is 10. Nowhere else to go, so I can just write my 10 into the next column, which would be my 10,000s. Get rid of that little 1, because we've used it. So the answer to 3 times 3,465 is 10,395. Now I'm ready to look at my next row, which is 20 times 3,465. But I want to just look at this 2 as a 2. It's very difficult to think about multiplying it by 20 every time. So how can I do that? Well, if I put a 0 here, I am making everything in this row 10 times larger, which means I can then just think of this 2 as a 2 instead of a 20. So we call this little 0 a placeholder. Now I don't need to think about multiplying it by 20, I can just multiply it by 2. 2 times 5 is 10, same rules. Next I can do 2 times 6, which is 12, plus my 1 equals 13. Get rid of the 1. Now I can do 2 times 4. 2 times 4 is 8, plus my 1 is 9. Get rid of the 1. And lastly, 2 times 3 is 6. So the answer to 20 times 3,460 is 69,300. Now I've answered my 2 individual lines, I've answered all my partition sections, now I need to smash it back together to get my final answer. So I can put my equals line, put an add sign, and here I go. 5 plus 0 is 5, 9 plus 0 is 9, 3 plus 3 is 6, 0 plus 9 is 9, 1 and 6 is 7. So there we have it, 3,465 times 23 is 79,695. Let's just think about things to remember for this. Always put your ones, 10, hundreds and thousands at the top of your place value chart so that you don't put numbers in the wrong place. Partition the question and the numbers into the little parts and write out those little questions on the side. That will really help you. Don't forget your placeholder. This little placeholder here is super important. If we forget it, it means that we're going to have a very different answer. And finally, once we've done the partition sections, add it all back together to get our final answer and get our tick. So now it's your turn. 2 questions here for you. Have a go at answering them and put your answers into the comment section. I'm going to try and mark every single one. Press pause on the video now. Good luck.
Okay, hopefully that wasn't too difficult. Let's get into our division now. We're going to be looking at how to divide by a 2-digit number. Ready?
Okay, so we have these 3 questions that slowly get harder. Let's have a look at our first question as we look at our steps. So our steps say to put the dividend inside and the divisor outside. So our dividend is this number, the number that we're actually dividing. So we're going to have 273 inside our bus stop, and then our divisor, which is this number here, the 13, on the outside. Okay, then step 2 says divide, and remainders go next door. We're going to be dividing using the number 13, so it makes sense to find a couple of multiples that are going to be in the 13 times table. So what I like to do is just write a little list next to my workings out. So I'm going to start with 13, after 13 would be 26, then 39, and sometimes I get to a position like 39 add 13, might be quite difficult. Well, I can just do a very quick addition question. 9 plus 3 is 12, 1 plus 3 plus 1 is 4. So I get my 42, then my next one I can see is 55, and I'm going to stop there. If we need any more, we'll do some more later. Okay, and we're going to use short method. So my first question says how many 13s are in 2? Well, as I can see quite clearly by my multiplication chart, we can't get any 13s out of 2. So I would put a 0, and now I'm going to look at 27. How many 13s are there in 27? So I can look down my multiplication chart and I can see we have a 13, we have another 13 that gets to 26, but obviously I can't go any higher than 26 because our number is 27. So I have 2. But we only managed to get to 26 and we needed to get to 27, so we have 1 left over. The difference between 26 and 27 is 1. So what am I going to do with that 1? I'm going to follow step 3 and put it next door. So now my 3 becomes a 13. And now I can do how many 13s are there in 13? Well, again, looking at our multiplication chart, you can see it's just 1. So my answer to 273 divided by 13 is 21. Okay, let's step it up a little bit and let's have a look at 3,245 divided by 34. So I'm going to set my question out just like before, and now I'm going to make a list of multiples of 34, and I'm going to start with 34, and it's going to be 68. And again, 68 plus 34 could be quite difficult, so I'm going to put a little quick addition. 4 add 8 is 12, 1 add 3 plus the 6 is 10, so my answer is 102. Then it'll be 136, and finally 170. And now I can begin. How many 34s are there in 3? 0, so I can just look at 32. How many 34s are there in 32? Also 0. So now I'm going to have to roll that whole 32 into the 4 as well and make it 324. And look at how many 34s are there in 324. Well, I didn't do enough multiplications for that, so I'm going to use some number knowledge. And I'm going to look at 34 and I'm going to multiply it by 10. 34 times 10 equals 340. And now I'm just going to go backwards down my multiplication table and do 34 times 9 would therefore equal 306, because I've just taken away 34 from the 340. So I can see from that there's going to be 9 34s in 324, but I only got to 306. So what's the difference between 306 and 324? Well, I can do 3, 2, 4, subtract 3, 0, 6. 4 subtract 6 can't do. 14 subtract 6 is 8. 1 subtract 0 is 1. 3 subtract 3 is 0. So the difference is 18. So I give my 18 to my neighbour, turning that 5 into 185. Now I can ask myself how many 34s are there in 185, and I can see that if I tried to add another number down here in my multiplication, it's going to be way bigger than 185, so I know that there's going to be 1, 2, 3, 4, 5. So my answer is 5, but that only took us to 170, so I can do 185 subtract 170 equals 15. So I would have a remainder 15. So my final answer is 95, a remainder 15. Let's have a look at a red chili challenge, a hard one, and let's follow the steps really quickly this time. So my dividend is inside and my divisor is outside, and I've got my 5 multiples ready if I need them. So now I'm going to look at how many 24s are in 6, 0. I'll look at it as a 65. How many 24s are in 65? Well, I can go 1, 2, but I could only get to 48 and I needed to get to 65, so I have a difference of 17. I'll put my 17 in front of my next number, turning that 4 into 174. Now I can see I need a couple more multiples. There we go. And how many 24s are there in 174? Well, I can see I can go 1, 2, 3, 4, 5, 6, 7. So I could get to 168. Therefore, the difference between 168 and 174 would be 8. Give my 8 to my neighbour. And my final question, how many 24s are there in 87? I can see that I can go 1, 2, 3. So my answer would be 3, but I could only get to 72, so the difference would be 15. And there we go, simple. Let's look at the things to remember. First, create a list of 5 multiples will really help you. Begin by dividing the first number in the bus stop, and then carry the remainders along if needed. Here are 3 questions for you to have a little look at. Put your answer in the comment section. I'm going to try and mark every single one.
Okay, there we go. That is looking at multiplication and division. Now let's look at how we can interchange those using inverse. Let's jump into it. Okay, we're going to be looking at 2 different style of questions here. We've got our green chili challenge, which is just a division question, and we're going to inverse it into a multiplication. And then we've got a missing number problem as well that we're going to see how inverse can help us solve. Okay, so let's start with our green chili challenge, our first question. So we have 15 divided by 5. So we know that if we have 15 divided by 5, we're going to get an answer of 3. There are 3 5s in 15. So what does inverse mean? Inverse essentially means the opposite. So division is the opposite of multiplication. So we can use these same numbers to create another number sentence, which is multiplication. So let's see how we can do that. But let's have a little think about what we know about number before we start. We know that when we're dividing a large number by a smaller number, we are going to get another small number, a number smaller than our first starting number. Therefore, it's logical to think that this number here, the 15, if we are making a multiplication question, will end up being the answer because 2 smaller numbers multiplied together will equal the bigger number. So therefore, my number sentence for my multiplication would be 5 times 3 equals 15. And let's check it, 5 lots of 3, yes, equals 15. But I can see another number sentence here that would also work. What if we flip the 5 and the 3 around and we used our commutative law? And I put 3 times 5, and I also know that 3 times 5 equals 15. So using the same numbers, so far I've made 1, 2, 3 separate number sentences. Well, I can actually see another one. I can see another division question because I think that if I get my 15 at the start again, and this time I divide by 3, I'm going to get 5. So with the same set of numbers, I've actually managed to create 4 number sentences, and these 4 number sentences together are called the number family. And every question will have a number family, a different way of expressing the numbers using different operations. In this case, we have 2 multiplication and 2 division questions. Let's have a quick look at another one. Let's say I have 25 times 4 equals 100. Okay, so if now I'm wanting to find the opposite, the inverse, I can try and think about my number knowledge again, and I can see that my larger number here is 100. So if I'm wanting to create a division question, I'm going to need to put my larger number at the start. So now I can have 100, and knowing what I know now about my number family, it doesn't matter which way around I put my 25 or my 4, because it's still going to be part of the number family. So I can say 100 divided by 25 equals 4. Or I could write 100 divided by 4 equals 25. Can any of you see the other question that I can have in this number family? I have 2 division and 1 multiplication, which means it must be another multiplication. And yep, I can see it here. I could have 4 times 25. Move those 2 numbers the other way around and I'll still get 100. Okay, so let's use that knowledge to try and help us with this missing number fact then. So here I have a question that says 12 times something equals 48. And this is a very common question that you're going to see in exams. So I can see this is a multiplication question. So I know that this number and this number will both be smaller than my 48. So therefore, for a division question, I'm going to put my 48 at the start. And I can simply use now the only number that I have available to me, 48 divided by 12. And I know that 48 divided by 12 is 4. Now I can check my answer by doing 4 times 12 should equal 48, which it does. So I've got now 1, 2, 3 of my number sentences. I can now get my other one, my other division question, by putting 48, but instead of dividing it by 12, I'm going to divide it by 4, which equals 12. But the one that really helped us was this one here in order to get our missing number. Let's have a look at another quick missing number. Let's say I put 50 and I divide by something, but it equals 10. And this one's a little bit different because I actually don't need to do the inverse operation because I have one of my division questions, but if I simply put my other division question, which would be 50 divided by 10, still in the same number family, that's going to equal 5. So therefore this question mark here could be replaced with a 5. Let's check it. 50 divided by 5 equals 10. Correct. Let me quickly get my next 2 number sentences and I can see that 50 is the largest number. So if I'm now going to multiply, that number needs to come to the end and I could work out that 5 times 10 equals 50, but also flip those numbers around. 10 times 5 equals 50. These are my number family. And there you go. That is using the inverse operation to help you solve both missing number questions and also being able to just check your answers and make sure you've got the correct answer. Let's think about the things to remember. Firstly, inverse essentially just means the opposite. Multiplication is the inverse of division, and addition and subtraction are inverse of one another. And then lastly, a number sentence can have a number family, and those number families can help you with all of what we've just been talking about. Okay, so now it's your turn. I would like you to try and find the 4 number family sentences for these 3 questions. Once you get them, put your answers in the comment section, and I'm going to try and mark every single one. Good luck. Okay, sometimes we don't get questions that are obvious where to start. So now we need a rule, and it's called the BODMAS rule. Ready? Let's learn. Okay, so what is the order of operations? Well, the order of operations is a mathematical principle, meaning the order that we need to do operations within a mathematical question. And we have this little term BODMAS to try and help us remember what order that is in. So let's have a look, and let's have a look at this question that we've got in the middle of the screen here. So our starting point would be here with the B, and our B stands for brackets. So the first thing we would have to work out in any question, if there is it, would be a bracket. Then our O stands for order, which is this little power of 2 here next to the brackets. And then the D stands for division. Our M is multiplication. Our A is addition. And our S stands for subtraction. But in this case, we don't have any subtraction, but that would come last. Now, in some instances, you might see BODMAS down here, where the I and the O are different. And in BODMAS, it just means index. Same principle, it still means this power of 2 here, but it's just taught differently in different places. So BODMAS, BODMAS, exactly the same thing. Okay, so let's follow our order of operations and try and solve this question then. So our first order is brackets. So we're going to solve the question in the brackets first. And in my brackets, I can see 12 divided by 3. Now, some of you might have noticed that our power of is connected to the brackets. But because it's not in the bracket, we're not going to do that at this stage. So I'm going to rewrite my next line, and it would be 4 plus. Now I can solve the brackets. So 12 divided by 3 is 4. And because now 4 is the only thing inside the bracket, I can actually now get rid of my brackets. It would be 4 to the power of 2 multiplied by 2. Okay, the next thing to do is the order, which in this case is this power of 2 here. So 4 to the power of 2 is just 4 multiplied by itself, so 4 times 4, and 4 times 4 is 16. So my next row would read 4
plus 16 times 2. My next one says division, and we actually don't have any more division in this question left, so I can move on to my multiplication. And my multiplication is this part here, 16 times 2. And the answer to 16 times 2 is 32. So my next row would be 4 plus 32. And I can now do my addition, and that's our last question actually. So I can now do 4 plus 32, and 4 plus 32 equals 36. So my total answer for this expression is 36. Okay, let's look at a harder one then. Let's look at this one here. And what's important to bring up now is that our division and multiplication and our addition and subtraction are linked. So although it says that our division will come before our multiplication and our addition should come before our subtraction, actually the case would be that if we get to a division or multiplication part, we would do it in the order that it's written. So if we were to look at this stage here, 4 divided by 2 times 3, I would actually start with my 4 divided by 2 because that's the first in the sequence. But if it read 4 times 2 divided by 5, then I would actually start with my multiplication because that's first in the sequence. So my division and multiplication are linked, and so is my addition and subtraction. So with that in mind, let's begin. And I'm going to start with this bracket first of all. Now in this bracket, I can already see that I have an order up here. So I'm going to do that part of the bracket first. So now my bracket would read 2 times 2, which is 4, plus 3 times 4 to the power of 2. Okay, looking back at my first bracket, there's no division in this question, so I can move to the multiplication. 3 times 4, which is 12. So I've got 4 plus 12 to the power of 2. Now within this bracket, I can finish off with my addition. And 4 plus 12 is 16, so it'll be 16 to the power of 2. And because 16 is on its own, I can actually get rid of that bracket, and I can simply work out 16 squared. And 16 times 16 is actually 256. So I'd end up with 256. Now I can move on to my other bracket, and I can see that in this bracket I'm going to have to work out the division first, which would be 4 divided by 2, which is 2. So I'd end up with 256 divided by 2 times 5 plus 2. And now in my next row I'm going to do the multiplication of this bracket, which is 2 times 5. So I'm ending up with 256 divided by 10. And now I've got rid of the bracket. And now I can see my question says 256 divided by 10 plus 2. And I'm going to have to work out the division first because that's first in my BODMAS before the addition. So I can do 256 divided by 10, which would be 25.6. And I'd have my plus 2. Now I'm ready for my final line where I can solve the final part, the addition, and 25.6 plus 2 equals 27.6, which is my final answer. So the final answer to this expression is 27.6, following my BODMAS rule. Okay, some things to remember then. So BODMAS can also be called BIDMAS. You might see it like that in some expressions, depending on whether we call it order or index. We must work in this order when solving any expressions. And then finally, the addition and subtraction, and then the multiplication and division, they are actually paired, and we would do those in the sequence that they appear in from left to right. Okay, let's now look at how to multiply and divide by 10, 100 and 1,000. This is a classic question that always comes up in the SATs, so let's pay attention to this one. Here we go. Okay, so we've got these 3 sets of questions here. They're going to get progressively more challenging as we go along. So let's first of all think about how we're going to do this and what we're going to use to help us. Well, we're going to start to think about our place value chart, and I've got one here for us now. And in our place value chart, you can see we have our ones, our tens, hundreds and thousands, and we could obviously keep going further and further that way forever. And then we have our decimal place, and we have values less than a decimal. So we have our 10th row, our hundredth, and our thousandth. Okay, so we're going to look at our first question. Our first question says 5.6 multiplied by 10. So the first thing to do is put our number into the correct places on the place value chart. And I can see that in my 5.6 I have 5 ones, a decimal, and then 6 tenths. And then all we're going to do is multiply it by 10. So we're going to be making this number 10 times larger. And what we should know about our place value chart is every single jump and every single column in our place value chart is 10 times larger than the one before it. So if we're multiplying by 10, we only have to move our digits 1 place. And we get a little hint with that because we have 1, 0 in 10. And which way are we going to move? Well, we know we're going to be moving up the place value chart to the left because we're getting a larger value, timesing. So here we go, let's start. I'm going to move my 5 one position here. I'm going to move my 6 one position here. And I'm going to put my decimal point back just for the sake of it. So now I can see that my answer to 5.6 times 10 equals 56. Okay, and let's look how it can help us with division as well. So my next question says 5.30 divided by 10. So the first thing to do is put our numbers in the correct place, and 5.30 is 5 ones, my decimal, 3 tenths, and 0 hundredths. And again, we're dividing by 10, so I'm only going to be moving one place, but this time I'm actually going to be moving my digits down the place value chart because I'm dividing, so therefore my answers are going to be getting smaller. So here we go, let's move them one place. My 5 now comes into the tenths column, my 3 goes into the hundredths column, and my 0 goes into the thousandths column. But now I need to put my decimal back, and I have a choice. I can either put a 0 here, or I could leave it without, but either way my value doesn't change. My answer is 0.530 or 0.530, and again this little 0 at the end, we actually don't need it, it doesn't change the value. So my answer in its simplest form is 0.53. Okay, let's get a little harder. We're going to look at timesing and dividing by 100. And first question says 23.1 times 100. First things first again, put our number in the correct place. And this time I'm timesing by 100, so I now need to think about moving my digits not one, but 2 places up my place value chart. So again, we're coming left or greater up the place value chart, but I'm going to move them 2 times. Here we go, my 2 goes 1, 2, my 3 comes 1, 2, and my 1, 1, 2. But now I have this gap before the decimal, and I need to fill this gap, otherwise I won't have a complete number, so I'm going to fill it with a placeholder or a 0. Therefore, my answer to 23.1 times 100 equals 2,310. Okay, next is my division. I have 453.2. There we go, all ready to begin, and I'm dividing by 100, so this time I'm not going to move up the place value chart, I'm actually going to be moving down the place value chart. So how many times am I moving? Again, 1, 2 zeros in my 100, or a different way of thinking about it, 100 times greater is going to be 2 columns across. So I'm going to start with my 4 and move it 1, 2, then my 5, 1, 2, my 3, 1, 2, and my 2, 1, 2. Very important that I don't forget to put my decimal back at this point. My decimal always stays on the decimal line. So my answer to 453.2 divided by 100 equals 4.532. Nice, let's start our hardest ones then. We have timesing and dividing by 1,000. First question says 8.71 times 1,000. So I'm going to put my 8.71 in the correct places. And now I'm timesing by 1,000. So hopefully we've caught onto the pattern. We've got 1, 2, 3 zeros in our 1,000. So I'm going to be moving them 1, 2, 3 places. Do the same to the 7, 1, 2, 3. Do the same to the 1, 1, 2, 3. And again, just like before, we have this blank column before the decimal, so we need to fill that in, and we're going to fill it with a placeholder. So my answer to 8.71 times 1,000 equals 8,710. Last but not least, 24.21 divided by 1,000. And again, we're moving 1, 2, 3 places. So let's begin. I have my 2 moving 1, 2, 3. My 4 will also go 1, 2, 3. Okay, but before I can move this 2, I can see already that I'm not going to have a column to move it into, so I'm going to create a new column, because remember our place value charts can go on indefinitely in either direction, and this will become the 10,000s column. And I think I'm going to need another one for the 1 that's next to it. So I add another one as well, and this will become the 100,000 column. Now I can carry on. I'll move my 2, 1, 2, 3 places into the 10,000, and my 1, 1, 2, 3 places into the 100,000s. But again, I can see a small gap here next to my decimal, which I must fill with a placeholder. So my answer to 24.21 divided by 1,000 is 0.2421. And there we have it. That is everything you need to know about timesing and dividing decimals by 10, 100 or even 1,000. Things to remember, always start with your place value chart. When you're writing the numbers in, focus on the value of each of the digits to make sure you put them in the right column. And remember that when we're multiplying, we move up the place value chart to our left, and when we're dividing, we move down the place value chart to our right. To know how many columns we're going to move our number, we can simply look at our question, and if we're multiplying by 10, that is only one position, 100, 2, 1,000, 3. And that number corresponds to the amount of zeros that are in the question. Okay, so here are a few questions for you to work on. Build your own place value chart and put your answers in the comment section. I'm going to mark them all. Okay, before we can look at prime factorization, let's look at what a prime number is compared to a composite number, because some people have not really heard these terms before. Let's go. Okay, so we're going to look at prime and composite numbers today, and we're going to be looking at 4 example numbers and working out whether they are prime or composite and why. Okay, but before we can do that, let's have a look at our definitions. So a prime number is a number with only 2 factors, 1 and itself, and we're going to discuss what that means in a minute. And composite numbers are numbers that have more factors than just 1 and itself, so a range of different factors. So let's look at our first example, the number 6, and let's discuss whether we think this is prime or composite. So if we go back to our definitions, we know that a prime number is a number with only 2 factors, 1 and itself, whereas the composite has more factors. So let's see what we get here. So we need to start with what is a factor. A factor is an integer, which means whole number, times by another integer equals the number that we're looking at, which in this case is 6. So basically, 2 numbers that multiply together to equal the number 6. So the first one we can always start with is 1 and 6. And at this point, if this is the only set of factors that we can get, then this 6 would be a prime number. But let's see if we have any more factors. Well, I know that 2 times 3 also equals 6, so therefore 6 is not a prime number. So our factors for the number 6 are 1, 2, 3 and 6. Now let's look back at our definition. 2 factors, 1 and itself, means it's a prime number, and more than just those 2 factors means it's a composite. So the number 6 is a composite number. Okay, let's have a look at the next one, number 7. So what are the factors of number 7? Let's do the logical sequence again. Let's start with the number 1 times 7. Can we do anything multiplied by 2? Well, no, because it's an odd number, and we know that odd numbers can't divide by 2. What about the number 3? 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, so no, 3 doesn't work either. What about 4? 4, 8, no. What about 5? 5, 10, no. What about 6? 6, 12, no. So then we're back to 7, and we end up with 7 times 1. And we know we don't need to do that because we've already got 1 times 7. So therefore, the only factors of the number 7 are 1 and 7. Okay, so let's look back at our definitions. A prime number is a number with only 2 factors, 1 and itself. And that's exactly what we've got here, 1 and itself, the number 7. So 7 equals a prime number. Okay, let's have a look at our next example, number 12. Now I'm going to let you in on a bit of a secret here, a bit of a top tip. We have an even number here. So by definition, we can always divide an even number by 2. So does it mean that no even numbers can be prime numbers? Let's check. So 12, I can start with 1 and 12, 2 and 6, 3 and 4, and then I'm back to 4, which means I don't need to do it. So I have 6 prime numbers, 1, 2, 3, 4, 6 and 12. So this is another composite number. Now let's just think about what I just said there. I just said all even numbers can't be prime because we can always multiply them by 2. But what about this number, the number 2? The number 2 can only be multiplied by 1 and 2. So therefore 2 is a prime number. And here's an interesting fact. 2 is the only even prime number. So that's something to remember. Okay, and let's look at question number 4. 19. So we know it's odd, so there's a chance that it can be a prime number. Let's see. So I can do 1 times 19. And now let's quickly go up our other multiplications. Can I do 2 times anything? No, because it's an odd number. 3, 3, 6, 9, 12, 15, 18. No. 4, 4, 8, 12, 16, 20. No. 5, 10, 15, 20. No. 6, 12, 18, 20. No. 7, 14, 21. No, 7 doesn't work. 8, 16, 24. No, 8 doesn't work. 9, 18, 27. No, 9 doesn't work. 10, 20. No, doesn't work. 11, 22. 12, 24. 13, 26. 14, 28. 15, 30. 16, 32, 17, 34, 18, 36. So therefore, we know that this is the only two numbers that can be multiplied together to equal 19. So this equals, that's right, a prime number. So let's go over the things to remember. A prime number is a number with only two factors, number 1 and the number itself. Most prime numbers are odd, except the number 2. That's right, well done. A composite number is the opposite of a prime number, and it's the numbers that have more than two factors. Let's have a look at these two questions. I want you to have a look at these 4 numbers and decide which ones are composite and which ones are prime. So have a look at these 2 sets of 4 numbers and decide which are prime and which are composite. Put your answers into the comment section below. I'm going to mark every one. Okay, hopefully you understood that, because we're going to use this knowledge of prime number to now look at prime factorisation, something that some people have never even heard of. So let's go. Okay, so we have these 3 numbers we're going to focus on today. We have the number 12, which is our green chili challenge. We have the number 36, our orange chili challenge. And then we have 750, our red and our hardest chili challenge. Okay, but first, what is prime factorisation? So prime factorisation is breaking down a number into its prime factors, which can then be multiplied back together to get the original answer again. But what does that mean? Well, let's start by getting some prime numbers on our screen to help us. So we've got these prime numbers here. These are the prime numbers all the way up to 20. 2, 3, 5, 7, 11, 13, 17, and 19. Now, if you haven't checked out my video on prime numbers yet, make sure you do that first, because we really want to get a good understanding of what a prime number is. But just to recap, a prime number is a number that can only be multiplied by the number 1 and itself. It has no other factors. So all of these numbers here can only be multiplied by itself and 1 to get that number. For example, number 7, the only factors are 1 and 7. 7 is not divisible by anything else, so therefore it's a prime number. Okay, now you might notice that the number 1 is not on this screen, and technically number 1 should be a prime number because it falls in the same category. It can only be multiplied by 1 and itself, but for technical reasons we're not going to get into in this video, it's not a prime number. Okay, so let's look at our green chili challenge and look at the number 12. So when we're looking for the prime factors, what we're trying to do is get our factor tree right the way down to prime numbers. Now, what does that mean? Well, what it means is we can get our 12 and we can find a set of factors. So let's do it with 2 and 6. 2 times 6 is 12. Now, what can we notice straight away? Well, we have the number 2, and 2 is a prime number. So we've already got that branch of our tree down to a prime number. But is 6 a prime number? No, it's not in our list, so therefore we need to carry on. And we can see that actually 6 isn't a prime number because it can be made up of 2 and 3. 2 times 3 equals 6. Now what do we notice? We've got ourselves down to a 2 again. 2 is a prime number, and guess what? Number 3 is also a prime number. So what we've done here is we've got our factor tree all the way down to prime numbers. So our prime factorisation for the number 12 would be 2 times 2 times 3. 2, 2, and 3. And if I multiply 2 times 2 is 4, times 3 is 12. Therefore, we know we've got it right. But wait a minute, I can hear some of you asking, what if we didn't start with 2 times 6? What if we started with another factor pair of 12? What if we started with, let's say, 3 and 4? Because 3 and 4 equal 12. Well, let's see what happens. Well, I've already got a prime number here, and now all I need to do is find the factors to 4, which would be 2 and 2. And 2 is a prime number, and therefore I can't go any further, and I actually have the exact same numbers as before. We have 3 times 2 times 2. 3 times 2 is 6, times 2 is 12. So we get the same answer. Okay, let's look at a harder one. Let's look at 36. Let's find our factors for 36. Now 36 is an even number, so we know that we can divide by 2, so let's do that. I'm going to start with 2 times 18. Okay, so have I got down to a prime number already? I think I have. I've got the number 2, so that side, that branch is done. Now I'm going to see if I can find a factor pair for 18. Well, again, 18 is even, so I can go 2 and 9. 2 times 9 is 18. And again, I found another prime number. Now 9 is not a prime number because it can be made up of 3 times 3. 3 is a prime number, therefore we know we've finished. So what are the prime factors of 36? We have 2, 2, 3, and 3. Let's check. 2 times 2 is 4, times 3 is 12, 12 times 3 is 36. Okay, a little bit harder because we had a little bit longer to do in our factor tree, but still not too challenging. Okay, let's have a look at one more. Let's have a look at our red chili challenge, 750. Well, this might look actually harder than it actually is because what we're trying to do is just find a factor pair. And one sensible starting position might be here to do 10 and 75 because 10 times 75 equals 750. But have I found any prime numbers yet? No, I don't think I have. 10 is not a prime number and 75 is not a prime number. So I need to keep going. I'm going to start with this branch here, 10. 10 can be made up of a 2 and a 5. Now have I found any prime numbers? Yes, I found the 2, which is prime, and I've also found the 5, which is also prime. Now I can look over to the other branch and I can say 75. Well, 75 will be made up of 3 and 25. 3 times 25 is 75. And guess what? I've found another prime number, but let's keep going with the 25 because that's not prime. 25 is made up of 5 times 5. And look what we've got. We've got our last prime numbers again because 5 is a prime number. So now I'm all the way down to my prime numbers. I factorized 750 into its prime factors. And the factors are 2, 5, 3, 5, and 5. And it doesn't really matter which way around we multiply this because as we know, multiplication is commutative. So I'm going to do 2 times 5 is 10, times 3 is 30, times 5 is 150, times 5 again is 750. And there we have it. Our red chili challenge actually wasn't too difficult at all. Okay, let's think about things to remember then. So we must always break our numbers into factor pairs. And then we're going to use a factor tree to go all the way down to prime numbers. And then the trick is that we can use these prime numbers to multiply them back together and we should end up with the original number. That's how we know we've finished our factorization and we've got to our prime numbers. Okay, I've got 3 questions here on the screen. Have a go at them, try and find the prime factors and put your answer in the comment section below and I'm going to try and mark every single one. Good luck. Whoa, that was pretty challenging, wasn't it? Hopefully you understood that. If you didn't, go back and watch it again because that's quite important. But for now, let's look at how to find the lowest common multiple. This is going to be something that's really important in our fraction knowledge. Let's start. Okay, we're going to look at these 2 questions, 5 and 12 and 3 and 11. But before we do that, let's first think about what lowest common multiple means. And let's think about it word by word. So multiple. A multiple means any number that is in the multiplication table of our given number, the number that we're discussing, in this case 5 and 12. So think about the numbers that are in the 5 times table, 5, 10, 15, 20, 25. They are all multiples of 5. And 12, 12, 24, 36, they are all multiples of 12. So a multiple is just the numbers that are in the multiplication table of the number that we're thinking about. Or a fancy way to think about it is a multiple is the product of our number multiplied by any integer, an integer being a whole number. So for example, 5 times 3 equals 15. 15 is the product, 3 was the integer we multiplied our number by, and therefore 15 is a multiple of 5. Okay? Common just means the same, together. So it means if I'm trying to find the common multiple, it wants me to find how many multiples are in both the 5 and 12 times table. And lowest simply means the smallest value. So we're looking for the smallest number that's in both of our multiplication tables. Okay, let's begin with question 1 then. And I have 5 and 12. So I'm looking for that common multiple, the lowest common multiple. So I need to think about what my multiples are. Let's think about our 5 times table. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, and 60. Let's stop there. And now let's think about our 12 and think about the 12 times table. So I would start with 12, 24, 36, 48, and 60. Okay, so I found my multiples, and now I think I've found a common multiple. I have this 60. And what I can also see that this is the only multiple that I have here, so therefore it is my lowest common multiple. So I could have carried on and I would have noticed that I would have also 120 in both of these multiplications, but that would not be my lowest common multiple because it's not the smallest number. The smallest number would be this one, the 60. So if we're looking at 5 and 12, the lowest common multiple, and we can say it like that, LCM equals 60. I give myself a tick. Now what you might notice with our lowest common multiple being 60 is that 60 is actually 5 times 12, our two numbers. 5 times 12 is 60. So we know that 60 was going to be a multiple, but we don't know if this is our lowest common multiple. So I'm not going to use this method. This method's great for finding a multiple, any multiple, but we don't always necessarily know it's the lowest common multiple. So it's much better to write down a sequence of our multiplication table so we can make sure we get the lowest common multiple. Okay, let's move on to question 2 then, and we have 3 and 11. Now what I think is quite a good tip is to multiply the bigger number first. So I'm going to find some multiples of 11. 11, 22, 33, 44, 55, and I'm going to stay there. And now I'm going to look for those multiples of 3. The reason I think this is a good idea to do it this way around is because now I know when to stop in my 3 times table, because hopefully I will bump into one of my multiples in the 11 table before I have to do too many. So let's go. I'm going to have 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33. Okay, what have I found? I think I found a common multiple. I found 33 in both the 11 times table and in the 3 times table. Now I can see that there's no multiple that's less than that in any of these digits, so therefore the lowest common multiple equals 33. So to find our lowest common multiple, all I need to do is try and draw a list of the multiplication table of both the numbers, find the ones that are common, the ones that are the same, and then look for the lowest one. Okay, I hope that was useful. Here are 3 questions for you. Try and find the lowest common multiple of all these sets of numbers and put the answer in the comment section. I'm going to try and mark every single one. Cool, now we've found our lowest common multiple, we can now find our highest common factor. Another really interesting principle and something that we really need to understand. Ready? Go. Okay, so where are we going to begin? Well, we're going to look at what the phrase actually says first of all, and we're going to think about these 3 words. Let's start with factor. So what is a factor? Well, a factor are any 2 numbers that when multiplied together equal the product of the number that we're talking about. So in this case we have question 1, we're looking at number 6 and number 15. So if any number multiplied together equals 6, they would be the 2 factors, and again for 15. So that's what factor is. Common just means the same, so we're looking for factors that are both in 6 and in 15, and the highest obviously means the highest, the biggest number, the greater value. Okay, so let's put that into practice a little bit and let's have a look at question 1 and let's have a look at these 2 numbers. So we're trying to find the highest common factor of 6 and 15. So first of all, let's look at the factors then. So if I have the number 6, how can we find our factors? If you haven't checked out the multiples and factors video on this channel, then this is your time to do that, because we're going to go quite quickly through what factors are here and how to find them, but there's much more description in that other video. So we know that the factors are 2 numbers multiplied together equals 6. So we can always start with 1 and 6. We know that 1 times 6 is always going to equal 6. So therefore 1 and 6 are both factors of 6. Okay, let's see if there's any more. Go logically in sequence. 2, and I know that 2 times 3 will also equal 6. Now let's see if I can go any further. Well, if I put 3, we know because I've got 3 here and I've already used a 3, that is as far as I should and could go. So my factors of 6 are 1, 2, 3, and 6. So now we need to look at 15. So if I put 15 over here, what are my factors of 15? Well, I know I have 1. 1 times 15 will equal 15. Have I got a 2? No, because 15 is not divisible by 2. I can't divide 15 by 2. So I have no 2. What about 3? 3 times 5 equals 15. What about 4? Is 15 divisible by 4? 4, 8, 12, 16, so no. And then if we try and use 5, I've already used a 5, so I don't need to do that. So let's have a look. Our factors of 15 are 1, 3, 5, and 15. Okay, so now that I found my factors, now I need to look at my next word, the common factors, and let's see which of those are the same. Well, in both of these I have a 1. In both of these I have a 3. And that's it. Okay, so I've found my common factors. And lastly, I'm looking for my highest common factor. So my highest common factor in this case is 3. So the highest common factor equals 3. Awesome, let's have a look at another question. Let's have a look at 8 and 16. So first of all, let's look for my factors of 8. I have 1 and 8, 2 and 4, 3 and 3, 6, 9. Nope, no 3. And if I try and do another 4, I'm just repeating myself, so I don't need to do that either. So here are my factors of 8. 1, 2, 4, and 8. Awesome. Now let's look at my factors of 16. I have 1 and 16, 2 and 8, 3. Is 16 divisible by 3? 3, 6, 9, 12, 15. No, doesn't look like it. So 4. And then what do we multiply 4 by? Another 4. So therefore, I know that I've come to the end because I've already now used that other 4. So my factors of 16 are 1, 2, 4, 8, and 16. Now let's look for those common factors. I have a 1 in both. I have a 2 in both. I have a 4 in both. I also have an 8 in both. So then now looking for my highest common factor, I can see that 8 is my highest common factor. Awesome. Okay, hopefully you're getting the gist of this. Let's finish off with question 3, which is 5 and 10. So let's start with 5. Factors of 5 would be 1 and 5. And then, do I have any more? 2. 2 times nothing. 2, no, 2 doesn't work. 3, no, 3 doesn't work. 4, no, 4 doesn't work. So we're back to 5. Well, we've already used our 5 and our 1, so we can't do that. So therefore, I only have these 2 factors. That makes 5 a prime number, which we're going to talk about more in our next video. Okay, so we only have these 2. Let's see what we have for 10. I have a 1 and a 10. I have a 2 and a 5. And then I think that might be it. 3, no, 4, no, and then we're back to 5. So my factors of 5 were 1 and 5. My factors of 10 were 1, 2, 5, and 10. Let's look for those common factors, and hopefully we can see we have a 1 that's common, and we also have the 5 that's common. Let's find that highest common factor, which we can now see is the 5. So the highest common factor equals 5. Awesome. Okay, well, hopefully this was useful for you. So what we're looking for, the highest common factor, first look for those factors, then let's find the common factors between the two, and then just look for that highest value, the biggest number. Okay, so here are 3 questions for you. Have a look at trying to find the highest common factor for these. Put your answer in the comment section, and I'm going to try and mark every single one. Awesome. Okay, there we go. Now let's have a look at what square numbers mean and how to do it. Okay, the first thing we need to understand is that squaring a number is essentially just multiplying the number by itself. So let's have a look at what that means, and let's have a look at this question here. We have 3 squared. So 3 squared is asking me to multiply this number by itself. So before we do that, let's just understand what these parts of the question are. The 3 is what we call the base, and the 2 the exponent. And what I'm trying to do when squaring is multiply my base by itself, the amount of times the exponent is telling me to. So in this case, I'm multiplying 3 by 3. So my number sentence will look like 3 multiplied by 3. And we obviously know that 3 times 3 is 9. So my answer to 3 squared is 9. But at this point, I want to show you what this actually means and why it's called squared. So I want to build a square here, and my square is going to have a width of 3 and a length of 3. Now if I get my square and now I cut it into its widths and length, so I've got 3 vertical squares and 3 horizontal, I can now see that my internal amount of squares equals 9. And that's essentially what we've just done. We've squared our number. So another way of thinking about how to square a number is how many squares would fit into that larger square if that large square has a width and length of our base number. So in this case, our base number was 3, so I've done a width and a length of 3, cut my square into those individual squares, and I got 9 as my answer. Let's have a look at it with another example. I have 5 squared. Now at this point, I want to share with you a very common mistake that people can make. In this scenario, a lot of people would multiply 5 times 2 because they think they multiply the base by the exponent, and that's going to give us an answer of 10. Which we can obviously see is wrong straight away. So my number sentence should actually read 5 multiplied by 5. And 5 times 5 is 25. Let's prove it again by building my square. 1, 2, 3, 4, 5 in length and 5 in width. And now if I cut this up into the individual squares, I can see that my internal amount of squares equals 25. Proving that 5 times 5 is 25 and that 5 squared is also 25. So hopefully this makes sense to you that 5 squared is essentially saying that we get a square with length and width of 5 and basically work out how many smaller squares we can chop that into using those measurements. Let's have a look at our last one, and we're going to do this without building up our square. We're going to do this the quick way. 9 squared is the same as saying 9 multiplied by 9, and 9 nines are 81. So the answer to 9 squared is 81. And if I was to take the time and build up my big square, we would be able to prove that. Okay, so what do we need to remember about how to square a number? Squaring a number is multiplying it by itself. And also, we call it squared because it is the result of chopping a square into those smaller squares. So now it's your turn. Have a go at trying to answer these 3 questions. Put your answers into the comment section, and I'm going to try and mark them all. Good luck.
Okay, so now we've looked at square numbers. The next step up, cube numbers. What are cube numbers? Let's find out.
So as you can see here, cubing a number actually just means multiplying a number by itself 3 times. So if we have a look at this first challenge here, 3 to the power of 3, we should first understand that this 3 is called the base, and this little 3 up here, the power of, we call the exponent. But in some places we know it to the power of, so we might say 3 to the power of 3, or 3 cubed. So, as it says here, to multiply the number by itself 3 times, what we should do with 3 cubed is say 3 times 3 times 3. And with a small number like this, we can work this out reasonably quickly. We can do 3 times 3, which is 9, and then 9 times 3 is 27. So that's pretty straightforward. 3 cubed equals 27. But I want to take the time to show you why it's 3 cubed and why it's 27 and what it all actually means. So if we draw a cube with a length, a width, and a height of 3, so we have 3 this edge and 3 this edge, and I can draw it in its 3rd dimension, and let's say we've got 3 down this back edge as well, we can see that when we chop it all up into its squares, that we have 9 on the first side, which is that first part of the question here, which is actually 3 squared. So 3 squared is 9. And then to find the cube, we would then multiply it by another 3 because we're actually going 3 deep. So we have this first row of squares, then we would have the next column, and we'd have a 3rd column. So we have to multiply that 9 by 3. So that's essentially what cubing means. But I promised you a quick way of getting there for numbers between 11 and 19. So let's have a look at this question here. Question 2 says 12 to the power of 3, or 12 cubed. So let's have a look. 12 cubed. Now the first thing we're going to do in this little trick is we're going to look at this digit here, and we're going to turn the digit into a letter. We're going to call the letter B. And then to work it out, what we're going to do is we're going to include the 1, so we'll start with the 1 here, and then we're going to have b, and then we're going to have b squared, and then b cubed. Once we've got these, the middle two we're going to double. Okay, so let's see what I mean, and let's work it out over here. So first one was 1. Then we need b. Well, b is just 2. And then we need b squared. B squared is 4. And then we need b cubed. And b cubed would be 2 times 2 times 2, which is 8. But like I say, we're going to double these middle two values, the tens and the hundreds column. So 4 doubled would be 8, and 2 doubled would be 4. And now I'm simply just going to add this up, treating it like any other addition question. So in my ones column, I have 8 and nothing, so that would equal 8. In my tens column, I have a 4 and an 8, which would be 12. I'm going to carry the 1 across, bring my 2 across. In my hundreds column, I have now a 1, a 2, and a 4, equals 7. And then in my thousands column, I have just a 1. And there you go. This is the answer. So the answer to 12 cubed equals 1,728. Do you want to see another one? Let's have a look. So let's have a look at 15 cubed. But this one's a little bit trickier, so just be careful when you're putting your numbers in the columns. But we're going to follow exactly the same process. We're going to first label this 5 a b, and then we're going to have a 1 to represent our first one, then a b, b squared, and b cubed. Now I can work it out. So I have 1, b on its own is 5, and now I can do b cubed, and b cubed is 25. But I only have 1 column width, so I'm going to put my 2 in this column over here, the higher value, and the 5 into the tens column. And that's the little detail that can be a little bit hard for people to remember. Let's do b cubed. Well, b cubed is 125, so now we've got even further to go backwards. Let's put my 100 in the hundreds column, my 20 in the tens, and now my 5 in the right column. Okay, but remember, we double the value of these two, so let's do that now. Double b is double 5, which is going to be 10, so I'm going to put 1 in this column and a 0 in this column to show 10. Double b squared is double 25, so that's 50. So now I'm going to put a 5 in this column and a 0 in this column. So it's starting to get a little messy, but not out of control yet. Okay, now I'm simply going to add it up. Let's do it. In my ones column, I've just got a 5. In my tens column, I have a 5 and a 2, 7. In my hundreds column, I have a 2, a 5, so that's 7, a 1 for 8, and a 5, 13. And in my thousands column, I have a 1, a 1, and a 1, 3. So my answer is 3,375. Pretty crazy, right? And that trick will work with cubing any number between 11 and 19 and sets us on our way for a little trick that we're going to look at in another video where we can look at how to find a cube between 20 and 100. Okay, so let's think about things to remember for this video then. Cubing a number is multiplying it by itself 3 times, and there is a trick for cubing numbers 11 to 19. Here are 3 questions for you to work on. Have a go at answering these. Put your answers in the comment section. I'm going to try and mark them all. Okay, that's a lot of learning. Now we're going to learn a couple of laws, a couple of rules that are associated to division and multiplication. First one is the commutative law. We might have seen this in addition and subtraction, but we're going to revisit it. Here we go. Okay, we're going to be looking at what the commutative property is, and we're going to be looking at these 4 example questions here and see how this rule or property applies. So first of all, we can think of the commutative property. Think of the word commutative like commute, which basically means to move. And what it's basically saying is that we can move our numbers in our questions and still get the same answer. And we can do this in both addition questions and the slightly trickier multiplication questions. So let's have a look what I mean exactly, and let's have a look at this addition question, 4 plus 6. When we have the question 4 plus 6, these two numbers are actually called addends. So we spell that like this, A-D-D-E-N-D-S. And it doesn't matter which way around we put these addends, we're still going to get the same number. Watch, if I put 4 plus 6, I'm going to get the answer 10. However, if I flick my addends the other way around and I put my 4 on the other side and my 6 at the start, add them still together. 4 plus 6 also equals 10. Let's look at it another way. If I have 4 balls, 1, 2, 3, 4, and I add 6, 1, 2, 3, 4, 5, 6, it gives me a total of 10. And it's exactly the same as if I have 1, 2, 3, 4, 5, 6 at the start, and 1, 2, 3, 4. I still get a total of 10. So addition questions are commutative. It doesn't matter which way round we put our question, we're still going to get the same answer. Let's have a look at it with this second example. 19 plus 100, 19 plus 100 equals 119. But if I flick my addends the other way and I have 100 at the start and I plus it to 19, I still get 119. And if I was a patient person and could draw out all those circles and balls, I could prove it with that model as well. Let's have a look at multiplication then and see if it works here as well. So 5 times 4. 5 times 4 is 20. But now my 5 and my 4 we don't call addends because we're not adding them. We call them factors because they are the factors of 20. And now let's see if I put these the other way around and put my 5 at the end and my 4 at the start. 4 times 5 also equals 20. Let's have a look at that with our footballs. And 5 times 4 can be shown like this. This array, as we call it in multiplication, represents 4 times 5. And 4 times 5 gives me a total of 20. But now if I flip this array around and put it the other way, this array now says 5 times 4. But we also now know that 5 times 4 still equals 20. So multiplication is the same. It doesn't matter which way round we put our question, we're still going to get the same answer. And let's demonstrate it with 8 times 11. 8 times 11 is 88, but also move mine the other way around. Start with 11 times 8, and 11 times 8 is also 88. So multiplication and addition are both commutative. It doesn't matter which way around we put the numbers in our question. Let's have a little think about subtraction and division quickly. Let's have a question, 5 subtract 3. 5 subtract 3 equals 2. Let's see if we get the same answer moving the digits around. And let's have 3 subtract 5. Well, 3 subtract 5, if I have 3 and take away 5, I'm going to end up in negative numbers. And I'm going to end up with negative 2. So I do not get the same answer if I flip these digits around in my question. So therefore, subtraction is not commutative. Let's have a look at division quickly. If I have 15 and I divide that by 5, I get 3. Let's move our digits around, and now I have 5 and I'm sharing it with 15. Well, this is actually quite a hard question to answer, but I know that my answer is 0.33 recurring, and again, definitely not the same answer. So again, division is not commutative. So addition and multiplication are commutative. Doesn't matter which way around we put our numbers in the question, but subtraction and division are not. Very important to remember. Okay, we're nearly there. Our last lesson is the distributive law. This is a really interesting rule and something that you use a little bit now in year 6, but way more as we go up into senior school. So make sure you're paying attention to this one. This one's a tricky one. Let's go.
So first of all, let's just think about the word distributive, because it's a bit of a horrible word really. We can think of distributive like distribute, or to share out. So what is the distributive property then? So we can look at a question like this first example, 14 times 6. And if we couldn't work out 14 times 6, or we didn't have time to do the written method, what we could do is we could distribute the numbers differently. And we could say that 14 is made up of a 10 and made up of a 4. And if I then multiply those individual numbers still by my 6, I can see I get 10 times 6 is 60, and 4 times 6 is 24. And then with my answer, if I simply add this up, 0 and 4 is 4, and 6 and 2 is 8. And therefore, I can get the answer 84. So this can become a very easy method of working out questions mentally. For example, if we have the question 432 times 5, this second example, 432 times 5 is obviously a difficult question to answer, but if I work out quickly what 400 times 5 is, then look at my 30 times 5, and then my 2 times 5. I can do those numbers quite easily in my head. 400 times 5 is 2000. 30 times 5 is 150, and 2 times 5 is 10. And now these numbers are quite easy to add up in my head. I can just add the 2000, the 150 and the 10 to get an answer of 2160. But that's not all that the distributive property is good for. It's also very good for these second two questions, of which this is meant to say 4, of course. So if we look at this first one first of all, 4 times 7 plus 5. I could work this out in the traditional way, using the order of operations and understanding that I need to solve the question inside the bracket first. So 7 plus 5 is 12, and then 4 times 12. And 4 times 12 is 48. Or I can use my new distributive property, and I can understand that in order to do this, I can distribute the 4 and multiply it by the 7. So 4 times 7 is 28, and 4 times 5 is 20. Add these two together, gives me a total of 48. And what you'll notice is it's the same answer in both of those. So the distributive property can be very useful for helping you understand and solve these expressions. Let's have a look at our last one. And again, we can use the order of operations and understand we have to solve the bracket first. 5 multiplied by 9. 5 9s are 45. Or I can use my distributive property and realize that I must first multiply my 5 times 3, which is 15. And then I can multiply 5 times 6 equals 30. Plus the two together equals 45. And again, same answer. So you can see how the distributive property can be very useful for helping to see the answer to expressions, especially when those expressions can get quite difficult. So there we have it. That is the distributive property within multiplication. Very useful for helping us with mental maths, but also to work out expressions. So what should we remember? Distributive is just a nice way of saying to distribute, or to share out, or move things around differently. Distributive property means to distribute or move the numbers around differently, and we can use this to help with mental maths and solve expressions easily.
And there you go, that is it. You have just completed all of multiplication and division year 6 maths. If you understood this and you can do it all, you are a genius, and I'll see you in another lesson. But if you didn't, go back, watch little bits again until you got it in your mind. And if you still don't get it, that's okay, you're going to see it in school. But hopefully this has been useful for you. If it has, give me a thumbs up, subscribe to the channel because we're going to be making loads of videos like this. Hopefully this was really helpful. I hope you do really well in your year 6 SATs. For now, peace out.